Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Assessing the Torsional Response of Elevated Water Tank with Amended Bracings Sujina Sahib S. M. Tech Student Structural Engineering Department of Civil Engineering Yanis College of Engineering and Technology Kollam, India. Abstract elevated tanks are important structures in storing vital products such as petroleum as well as water. Elevated storage tanks are commonly used to secure constant water supply from longer distance under the effect of gravitational force. They are constructed in such a way that its greater portion of their weight is concentrated at an elevation. Torsional failure of elevated water tanks in past earthquakes has highlighted the importance of this problem. Modeling and analysis of elevated water tanks should be done using ETAB software. Seismic response spectrum, equivalent static analysis and modal analysis were conducted. Different staging configurations consist of staging with different altered longitudinal bracings are provided. Through this study an effective approach to reduce torsional effect must be formulated. Tank responses including local torsion, global torsion will also be calculated. Keywords: elevated tanks, bracings, local torsion, global torsion, ETAB software. Introduction. Water tanks are one of the most important lifeline structures. In most of the cities and rural areas, water tanks forms an integral part of water supply scheme. Types are underground water tanks, ground supporting water tanks and elevated storage water tanks. Elevated water tanks are mostly used. The elevated water tanks are also known as overhead supply reservoir, OHSR, elevated supply reservoir, ESR, etc. To secure constant water supply from longer distance under the effect of gravitational force, the elevated water tanks are necessary. They have low ductility and energy absorbing capacity as compared to the conventional buildings. They get heavily damaged during earthquake due to the fluid structure interactions. Presence of heavy rooftop masses like water tanks increases the seismic forces in the members of a building. They constructed in such a way that a greater portion of their weight is concentrated at an elevation. So seismic safety of liquid storage tanks is of considerable importance. Damage to these structures during strong ground motions may lead to fire or other hazardous events. Reinforced concrete water tanks can be made economical, monolithic, and watertight by their design and construction. Different types of bracings configurations can be provided to the staging for adequate resistance of seismic forces. 2. Objective: to find out the torsional behavior of the elevated water tank by altering the longitudinal geometry of the braces. 3. Methodology. 4. Modeling table. Design data of water tank, Patel et al., 2017, SL.NO1234567891011121314, component: top slab, bottom slab, 230 mm x 230 mm, height of staging, height of container, dimension of tank, zone factor, importance factor, reduction factor, type of soil bracing, type beam column bracing, values 150 mm 200 mm 150 mm 15 m 5 m 6 x 6 m 0.36 v 1.5 for water tank. 5 SMRF medium soil X bracing 230 mm x 300 mm 300 mm x 300 mm 230 mm x 230 mm. Table 2. Wind loads is 875. Part 3. Type: basic wind speed, VB, probability factor or risk coefficient, K1, terrain, height, and structure size factor, K2, topography factor, K3, structure class value 50 m/s 1.06 1.07 1.0b. Source: clause 5.2, clause 5.2.1, clause 5.2.2, clause 5.2.3, clause 5.3.2.2. IJERT 10 is 060183 www.ijert.org 369. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 B5 B6 B7 Fig.1. Plan, elevation, and 3D view of water tank. A modification of bracing geometry. In the present study, modeling of 8 different types of altered longitudinal geometry of the braces. Only depth of the bracings are varying. Width remains the same. Length of bracings provided is 4.24 m. Dimensions of large cross-section provided is 230 x 230 mm. Dimensions of small cross-section provided is 230 x 76.67 mm, that is 1/3 RD of the depth. In the present study, 1 normal bracing with 230 x 230 mm uniform cross-section and 8 altered longitudinal geometrical bracings are modeled and analyzed. From the 8 models, all the models are symmetrical bracings. From this, 4 models, B1 to B4, are designed in such a way that it is divided equally into 3 portions for altering the depth, and in case of B5 to B8 bracings they divide it into 3 portions and the middle portion again divides equally, so total of 4 portions for altering the depth. B1, B2, B3, B4, B8 Fig 2. Altered longitudinal geometry of the braces via analysis. A equivalent static analysis. The equivalent static lateral force method is a simplified technique to substitute the effect of dynamic loading of an expected earthquake by a static force distributed laterally on a structure for design purposes. As per IS 1893:2002, torsion should be considered when ratio of maximum story drift to average story drift of the structure is more than 1.2. Table 3. Drift ratio model ID max drift / average drift NB 1.332 B1 1.314 B2 1.324 B3 1.308 B4 1.319 B5 1.319 B6 1.308 B7 1.327 B8 1.308 1.78 1.77 1.79 1.32 0.98 0.97 0.56 0.33 B1 B2 B3 B4 B5 B6 B7 B8 Fig.3. Percentage reduction in torsion W.R.T normal bracing IJERT 10 is 060183 www.ijert.org 370. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021. For all models the maximum story drift to average story drift is greater than 1.2. Model with normal bracing have maximum torsion. Model B3, B6, and B8 have the maximum reduction in torsion. B-modal analysis. Modal analysis is used to determine the number of modes and corresponding mode shapes. Loads are applied as acceleration in X and Y direction. 12 number of modes are taken for analysis. At mode 12, mass participation ratio is approximately 100%. The effective mass participation factor represents the percentage of the system mass that participates in a particular mode. It provides a measure of the energy contained within each resonant mode. Type: eigenvector modal analysis. No of modes equals 17 at 99% mass participation 32 32 32. The global torsion get reduced maximum for bracing B8. The torsion is less for bracings with least cross-sectional area near the supports. The torsion is highest for bracing with largest cross-sectional area near the support too. Local torsion. Local torsion refers to the torsion in each bracings. 76.07 56.31 66.31 55.48 63.81 31.90 40.36 29.05 25.6 17.6 18.4 12.8 9.6 B1 B2 B3 B4 B5 B6 B7 B8 Fig 4. Percentage reduction in torsion W.R.T normal bracing. The time period at torsional mode get reduced maximum for bracing B3, B6 and B8. Model with normal bracing have maximum torsion. The torsion is less for bracings with least cross-sectional area near the supports. The torsion is highest for bracing with largest cross-sectional area near the support. See response spectrum analysis. Response spectrum analysis, RSA, is a linear dynamic statistical analysis method which measures the contribution from each natural mode of vibration to indicate the likely maximum seismic response of an essential elastic structure. Seismic zone factor equals 0.36. Soil type equals 2. Damping ratio equals 50%. 1. Global torsion 71.17 55.07 77.77 70.62 60.64 76.12 53.18 84.21 B1 B2 B3 B4 B5 B6 B7 B8 Fig.5. Percentage reduction in global torsion W.R.T normal bracing. Global torsion refers to the torsion of the entire building. B1 B2 B3 B4 B5 B6 B7 B8 Fig.6. Percentage reduction in local torsion W.R.T normal bracing. The local torsion get reduced maximum for bracing B8. Model with normal bracing have maximum torsion. The torsion is less for bracings with least cross-sectional area near the supports. The torsion is highest for bracing with largest cross-sectional area near the support. 3 brace reactions. Torsion axial force 56.31 66.31 55.48 63.81 76.07 40.36 31.90 29.05 17.44 9.03 19.51 20.78 21.00 11.40 13.43 7.54 B1 B2 B3 B4 B5 B6 B7 B8 Fig.7. Percentage decrease of axial force with respect to normal brace torsion. Shear force 76.07 66 56.31 63.81 56.31 55.48 47.69 40.36 39.49 35.90 31.90 26.15 30.26 32 91 70 59 22.5 65.64 B1 B2 B3 B4 B5 B6 B7 B8 Fig.8. Percentage decrease of shear force with respect to normal brace. IJERT 10 is 060183 www.ijert.org 371. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Torsion bending moment 76.07 62.00 56.31 66.31 60.00 55.48 63.81 60.00 31.90 15.00 40.36 46.00 29.05 20.00 22.00 2.00 B1 B2 B3 B4 B5 B6 B7 B8 Fig.9. Percentage decrease of bending moment with respect to normal brace axial force and shear force are proportional to brace torsion. For braces with less cross-sectional area near the supports, bending moment decreased by 15 to 46%. 11 PLN Saraha and V.S. Rao, Comparative Study of Analysis of Elevated Water Tank Due to Earthquake from Different Zones of Earthquake, International Journal of Constructive Research in Civil Engineering, Volume 2, January 2016 12 A. Anasati, Dr. M. S. Kiddu, Seismic Investigation of RCC Elevated Water Tank for Different Types of Staging Patterns, International Journal of Engineering Trends and Technology, IJET, Volume 14, August 2014 13 GP Deshmukh, A.S. Patekad. Analysis of Elevated Water Storage Structure Using Different Staging System, Indian Journal of Science and Technology, Volume 9, August 2016 14 PIN Sarahavanka. Srinivasa Rao, Comparative Study of Elevated Water Tank Due to Earthquake from Different Zones International Journal of Construction Research in Civil Engineering, Volume 2, Issue 1, 2016, ISN 2454-8693 15 H.T. Patil, Rajashakhar Tekatai, Comparison of Seismic Behavior of Rectangular Elevated Water Tank International Journal for Scientific Research and Development, Volume 3 Issue 05, 2015, ISN, Online 2321-06136. Conclusion: staging with same cross-sectional area throughout the bracing have maximum torsion. The torsion is less for bracings with least cross-sectional area near the supports. Brace axial force and shear force are proportional to brace torsion. For braces with less cross-sectional area near the supports, bending moment decreased by 15 to 46%. By reducing the cross-sectional area near the support, reinforcement and cost of the bracing can be reduced. References 1C and Patel, S. N. Vatala, H. S. Patel, Sloshing Response of Elevated Water Tank over Alternate Column Proportionality International Journal of Advanced Engineering Technology, Volume 3 Issue 4 October 2012 2 V. Verer, S. B. Vankudar, P. Prabhavati, Optimization of Water Tank The International Journal of Science and Technology, Volume 2 Issue 7 July 2014 3. N. J. Singh, I. Mohammed, Design Analysis and Comparison of INSA-type Water Tank for Different Wind Speed and Seismic Zones as per Indian Codes, International Journal of Research in Engineering and Technology, Volume 04 Issue 09 September 2015 4 S. Wonkhead, P. J. Salunk, N. G. Gore, Cost Optimization of Elevated Circular Water Storage Tank, The International Journal of Engineering and Science, Volume 4, Issue 2015 5 H. Mohammed, Optimization of Water Storage Tank, International Journal of Engineering and Technical Research, Volume 3, Issue April 4, 2011 6 F. Asari, M. G. Vanza, Structural Control System for Elevated Water Tank, International Journal of Advanced Engineering Research and Studies, Volume 1 Issue 3 April-June 2012 7 A. N. Asadi, M. S. Kiddu, S. R. Asadi, Seismic Analysis and Optimization of RC Elevated Water Tank Using Various Staging Patterns International Journal of Engineering Research and Application, Volume 6 Issue 7, Part 1, July 2016 8 Essay. Barakat, S. Altubat, Optimization of Elevated Water Tank The International Journal of Science and Technology Volume 2 Issue July 7, 2009 9 S. Siddiqui, B. K. Singh and P. Thakur, Performance-Based Seismic Analysis on RCC Framed Elevated Circular Tanks with Flat and Domical Bases, Indian Journal of Science and Technology, Volume 9, August 2016 10 Swathi C. Naik and M. S. Bandewad, Seismic Analysis and Optimization of a Rectangular Elevated Water Tank, International Journal of Man. Machine Interface, Volume 4, July 2016. IJERT 10 is 060183 www.ijert.org 372. This work is licensed under a Creative Commons Attribution 4.0 International License.